this lecture, we will discuss inverse functions, and later on, we will talk about exponential functions. So, to start with inverse functions, well, an inverse function of a function given by, let's start with the simplest one, which is a list of ordered pairs. So, suppose we have this function given in this form, and we know how to check whether this is a function or not. So basically, every domain or every element of X element is paired to one and only one Y element. And the domain of this function is the X values, which are 5, 7, 9, and 11. And the range for this function is the Y values. So we have, sorry about that. We have, so we have this list of elements. Now, the inverse will switch this one, okay? For the inverse function, the domain of f becomes the range of the inverse of f, and the range of f becomes the domain of the inverse function. Therefore, we write f inverse, well, we just flip this. 544, it becomes 44.5. 756, it becomes 56.7, and so on. So basically, this is what we call an inverse function, okay? We just switch the domain and the range. And graphically, to look at this one, if we plot these ordered pairs on the xy plane, what we find or what we get is something like this one. For example, 5,44 and 7,56, 9,68, 11,80. And if we connect these points, we will get a line something like this, right? It should be a straight line, of course. But the line goes something like this, okay? And now, if we interchange these two numbers, 5,44, if I bring 44 first and 5 next, then we get this point will come to this point if we switch the two numbers. So it becomes 44,5. And 756 becomes 56.7, and the point goes to this point, and so on and so forth. And again, if you connect these points, you will get a straight line that looks like this one. And these two lines, they are a reflection of each other along this line. And this line is called the y equals to x line, okay? So the graph of two inverse functions is a reflection of this. So here, this is when our function is given in this form, in an ordered pair form, okay? But this is not only the case, because sometimes, not only sometimes, most of the time, the function is given in the form of an equation. Now, before we go to that, first let's discuss a one-to-one function. Now, a one-to-one function is a function, let's say for a and b in the domain of f. When a and b are different, then f of a and f of b has to be different. Or if f of a and f of b are equal, then that should imply a and b are the same. Okay, so that basically what we are saying is for every two elements in the domain, the range should be different. Okay, they have to map to different points. Otherwise, it's not one-to-one. Now, based on this definition, let's determine if these two functions are one-to-one or not. So for the first one, we have f of x equals to negative 4x plus 1. And by definition, if f of a equals to f of b, if we have this one, and this should imply this one. Okay, now let's start with this one. Let's pick a and b, any arbitrary elements. So f of a, if I replace x by a, then I will have f of a equals to, and then again I will replace b in here, f of b. But f of a means we replace this one, negative 4x plus 1, and f of b, replace this x by b, negative 4b plus 1. Now 1 will cancel out because we subtract negative 1 from each, so they cancel out. So we have negative 4, oops, this has to be a. This is a, sorry. Okay, we have this one. And again, if we divide both sides by negative 4, they cancel out. So we have a equals to b. So we started with this one. We started with this one, and then we showed that if this is true, then this is true. Therefore, this is the definition of a one-to-one function. So we showed that this function here is a one-to-one function. And well, this is a linear function. This is a straight line. And for any linear function, or any linear function, is a one-to-one function. Okay. Here we showed only for one specific function, which is given by this form. But in general, any linear function is a one-to-one function. Well, not any linear, because sometimes we may say a constant function is a linear function. Some may argue that we have this constant function. So this is not true for this one. For if it is a horizontal line, then it's not a one-to-one function. But in general, other than this horizontal line, if we have any line like this one, they are a one-to-one functions. Okay, how about the next one? Suppose we have g of x equals to absolute value of x minus 3. Now let's try to show if f of a equals to f of b, then does it mean a equals to b? Well, let's see. Now g of a, we start with g of a equals to g of b. G of a is, we replace x by a, so we have absolute value of x, absolute value of a minus 3 equals to absolute value of b minus 3. And then, well, they will cancel out, so we have absolute value of a equals to absolute value of b. And what does this mean? Well, if we go back and if we try to remember what this means, we learn absolute value equations. So this means a equals to plus or minus b. Well, what we learned was a is b or a is negative b. Okay, so basically this means a equals to plus or minus b. In this case, this doesn't mean a equals to b. This doesn't necessarily mean a equals to b. Okay, therefore this is not one-to-one function. Okay. Okay, and if we have the graph of the function, there is another way of checking whether the function is a one-to-one function, and this is called the horizontal line test. The horizontal line test tells us that when we have the graph of any function, if a horizontal line doesn't intersect at more than one point to the graph of the function, then the function is a one-to-one function. For example, well, we have here, if we look at this point, one is here, two are here, and if you draw a horizontal line at this point, then this horizontal line touches these 2 points. which means it's touching this function at more than one point. Therefore, this is not a one-to-one function. And if we look at this one, if you draw any horizontal line or at any point, you can try whatever horizontal line you want. You can never touch any two of these points, two of them, right? So each line will touch at most one line, one point at most. Therefore, this is a one-to-one function. And graphically, let's say we have the blue lines, and drawing horizontal line at any point or at any level, it touches the graph only once. Therefore, this is a one-to-one function. This one, let's say if I draw a horizontal line here, it touches the graph only once, right? But if I draw another line here, it touches the graph at two different points, and here at two different points. Therefore, because of this one, since we found some area or some points that are touched by one straight line, by one horizontal line, then this is not a horizontal line. Just one line is good enough to fail this function not to become a one-to-one function. And again, we have this. And if you draw a line here, well, this one, based on this, it's not a one-to-one, right? But before checking whether this is a one-to-one function or not, we have to check whether this is a function or not. And for a function, to determine whether a graph represents a function or not, remember we had the vertical line test. And the vertical line test is, for example, if we have a graph like this one, and if a vertical line intersects the graph of the graph of this or the graph at more than one point, then we say this is not a function. And similarly, if you look at this one, if you draw a vertical line, it touches the graph more than once. Therefore, before we check whether it's a one-to-one function or not, we check whether it's a function or not. So this fails the vertical line test, which means it's not a function. And if it's not a function, we don't need to test whether it's one-to-one function or not, because the one-to-one is only for functions. So this is not a function. Okay, we're not saying it's not one-to-one, but we are saying it's not a function. Okay, now how do we determine whether two functions are inverse of each other or not? Well, suppose we have f and g, okay, two functions. Let's call them f and g. And if you remember, we learned this f of g of x, which is composition of two functions. Now, if f and g are inverse of each other, then f of g of x, the composition of this f and g, is x for all x in the domain of g, and the composition of g of f of x is x for all x in the domain of f. Okay, so this is how we can test whether, or how we can determine whether two functions are inverse of each other or not. For example, let's consider these two functions. And we have f given by f of x equals to 4, and g of x is x minus 4 over 5. So based on this definition, I will check if these two functions are inverse of each other or not. So let's start with the property number 1. F of g of x, okay? This is f of x. This is basically means f of g of x. And g of x is this one, so I will plug this one in here. 5 times x minus 4 over 5 plus 4. Okay, So this will cancel out. We have x minus 4 inside, and then we have plus 4, and minus 4 plus 4 is 0, so we have x, and that's what we have right here. Therefore, this is true. And the second is g of f of x, and this is g of f of x. So we substitute f of x as a whole, this in place of x. So that becomes 5x plus 4 minus 4 over 5. We replace x by this one here. Okay. So here, here 4 minus 4 is 0. So we have 5x on top over 5. And again, this will cancel out. So we have x. And again, that's what we have right here. Therefore, f and g are inverse of each other. Okay. Now, how do we find an inverse? So this is just to check whether two given functions are inverse of each other or not. But let's say we have a function. Now, how do we find the function, the inverse of that function? Okay. So I have this function, and I'm asked to find the inverse of this function. So the first thing that we need to do is we replace this f of x. I will change this function notation as notation to an equation of two variables. So I will replace this by y. So what I'm going to do is I will write y equals to x minus 2 over x plus 2. We just replace this one by y. And then the next is we interchange y and x in this equation. Okay, here bring x here and replace this, change this x by y, both of them. So that will become x equals to y minus 2 over y plus 2. Okay, and the next is now we solve for y. From this one, we solve for y. And solving for y is now we multiply both sides by y plus 2. So we have x equals to y plus 2. And we have y minus 2 on the right side. So I will distribute this one. xy plus 2x equals to y minus 2. So the aim is to solve for y. We have it here. Therefore, we have to bring like terms to one side. Therefore, I have x, y minus y equals to, I'll take this one to the other side, minus 2x minus 2. And factor out y, x minus 1 equals to minus 2x minus 2. And here we divide both sides by x minus 1, and we get x equals to minus 2x minus 2 over x minus 1. Okay. We can write this one as, I'll write it here. We can write this. This is the same with 2x plus 2 over 1 minus x. Okay, they are the same. Okay, and the next step after solving for y, the next step is now we replace this y by f inverse of x now. Okay, so our y here is just replace this one, f inverse of x. This is how we represent the inverse of the function f. So originally f of f was this one. This is the original function. Now instead of writing f, we put -1 up here. So that will mean this is an inverse of this function. Okay, we always use the same notation. If this is f, we use f, and to show it is an inverse, we put here -1. And this is given by we can just use this one, minus 2x minus 2 over x minus 1. Okay, so this is the inverse function of this one, and you can test this to check whether this is the actual inverse or not. Okay, we can use the properties using the composition of the inverses to see whether this is indeed the inverse or not. Okay, so now we learned what an inverse of a function means and how we can find inverse of functions. And the next is exponential functions. Now, what is an exponential function? Well, an exponential function is a function which is given in the form of f of x equals to b to the power of x, where b is a constant. B could be between 0 and 1, or b could be greater than 1. Okay, we don't want b to be 1. B should be different from 1, and b cannot be less than 0. Okay, b cannot be less than 0. Less or equal to, actually, b cannot be less or equal to 0. Okay, so the value of b, well, b is a constant, and the value of b can be greater than 1 or between 0 and 1. And here we have x. Okay, so the b is called the exponential, the base of this function, and the function is called an exponential function of base b. Okay, for example, let's say we have f of x equals to 2 to the power of x. Now 2 is a positive and 2 is greater than 1, so this is an exponential function. F of x is an exponential function. 1/2 to the power of x. Again, this is exponential function because this 1/2 is between 0 and 1. Okay, f of x equals to -2 to the x. This is not an exponential function because this b, this -2, is less than 0. F of x equals to x squared. Again, this is not an exponential function. This is a polynomial function. The reason why this is not an exponential function is because this is not a constant. This is a variable. This is the constant. Okay, they are interchanged. So this is polynomial function, not exponential function. F of x equals to let's say √3 to the power of x. Well, this is an exponential function because this number, it is a positive number and it's greater than 1. Therefore, it is exponential function. Okay, so these are just simple examples of exponential function, just by the definition, from the definition of an exponential function. Now, if we have an exponential function, how do we graph this kind of functions? So first, it's important to learn the properties of graphs of exponential functions. So for an exponential function given by this form, we can have two different graphs. When I say two, based on whether it's decreasing or increasing or increasing. Okay, so if b is, remember we have two different range of values for b. One is greater than 1, another is between 0 and 1. So if b is greater than 1, we have an increasing function that looks like this one. Okay, like this one. This is for b greater than 1. And if b is between 0 and 1, then we have a graph that's a decreasing graph like this one. So this increasing graph is called exponential growth function. and it has application in business, in economics and stuff. And the other one is a decreasing function, and it's called an exponential decay. Okay, both of them, they are useful in many applications. And the domain of any exponential function is the whole real set of real numbers, and the range is between 0 and 1. Okay, because both of these graphs, they never pass the x-axis. They get closer and closer and closer, and they never touch the x-axis. Therefore, the range is always above 0, which is why we have 0 to infinity. And the x-axis is called the horizontal asymptote because the graphs on both directions, they never touch it. Maybe here it looks like they touch it, but in reality, they don't touch it. They get closer and closer and closer, this one on the right side and this one on the left side, but they never touch it. That's why we call it a horizontal asymptote. And the function passes through this point. All the exponential functions, they pass through this point, and this point is 0, 1. Okay, and the reason why is because f of 0, because at this point on this line, x is 0, so f of 0 is b to the power of 0. B could be any number, it doesn't matter. Any b to the power of 0 is always 1. So 0, 1, any graph of exponential function passes through this point. So these are the properties of an exponential function. And if we know these properties, then it could be much easier to draw the graph. So an example is, here we have f of x equals to the power of x. As you can see, the base b here is 2, which is greater than 1, and we have an increasing function, which is an exponential growth function. And here we have 1/2 as base, so 1/2 to the power of x. It gives us a decreasing function, which is an exponential decay. And this is just simply to represent or to show the graph when b is between 0 and 1, and the graph when b is greater than 1. And if we have, of course, if we have any function given as an exponential function, then we can use the listing method. We can prepare the table of values, and then we can just spot out the points, and then we can just connect them. Okay, that's one way. And another way is we can use the shifting method. Okay, shifting or transforming method. And for example, here we are asked to graph g of x equals 1 to the power of 1 over 4 to the power of x minus 2 plus 1. So this plus 1, well, first let's look at this. If we have this one, so this is the base function here, and for this one, since b is between 0 and 1, we know that the graph of this function is a decreasing function, which is the blue line. And then this minus 2 shifts the graph to the right by 2 units. Okay, and that takes, you can take some arbitrary values here. For example, this point will go to this point, and this point goes to this point. Okay, and then we have this graph, and this is 1 over 4 y equals 1 over 4 to the power of x minus 2. Okay, and then we have another shift, which is plus 1. We add to the red line, we add 1, and adding 1, it shifts this graph up by 1 unit. Therefore, we come here. So take one arbitrary point. This will go up here, and then we have this green line, which is the graph of this function. Okay. Therefore, if we add some values in here, those will shift the graph left or right. So if this is minus, then it goes to the right. If this is plus, it goes to the left. And if we add a constant here or subtract a constant here, adding means it goes up, subtracting means it goes down. All right. And now we will see this very important number in mathematics, which is called the E, which is represented by the letter E. And well, you can try this at home using your calculator or your laptop. This formula, for example, we have 1 plus 1 over x to the power of x. If you try this number, if you calculate this, evaluate this expression for different value of x, and if you increase the value of x, let's say you start with 1, then you go to 50, 100, 1000, 10,000, and so on and so forth. As the value of x increases, this number converges to some special number. As you can see here, it starts at 2.7048 something, then 2.71, and it goes, and then here it's kind of getting kind of step. So 2.718 to 8, then 18 to 17. Okay, so somewhere around this number, this is what we call the letter E, or the number E, not letter, the number E. And this number E, approximately, we can kind of round it. So approximately it's 2.71828. But it goes forever. It's not a fixed number, or it's not a rational number. It's irrational number. And this one, we call it the natural base E. And this is what we call the natural base. We will learn this one in the next section, which is logarithms. Now, if we use this number as a base for exponential functions, then we have a natural exponential function, which is, this is, for example, the graph of y equals to e to the power of x, because e is approximately this number, and this number is greater than 1, so the graph is an increasing function, right? Therefore, we have an increasing, a graph of an increasing exponential function. And the reason why we are learning this one is because it's very useful in calculations, in applications, or it has applications, for one of which is we use this in calculating compound interest. Okay, and to explain this one, let's consider, suppose that P dollars is invested or borrowed at an annual interest rate of R for T years. Okay, and now the simple interest is given by this formula. I equals to I is the simple interest, will be the P times R times T. But if the interest is compounded n times a year, if we have compound interest n times per year, then A becomes P times, P is the principal amount borrowed or invested, P times 1 plus R over N to the power of N times T. Okay, and this depends on what N is, how many times it's being compounded. As it increases, this N increases. And if it becomes continuous, instead of just taking 365, it becomes, if the compounding is continuous, then this becomes a equals to p to the power of p times e to the power of r times t. And as you can see, here is the important number e. Okay, because this number, I'm not going to show you the derivation here, but you can show the derivation of this one. It's in our book. You can, if you are interested, you can go and see how we go from here to here. Okay, you can show how we get this formula. So this is the compound interest when it's compounded continuously. Okay. Now let's look at this example. Suppose that 10,000 is invested with 4% interest for 5 years under the following compounding options. Complete the table. Now we need to complete this one. So here the principal P is 10,000 and the interest rate is 4%. If we change this one to decimal, it becomes 0.04, and T time should be in years, so it's 5 years. Therefore, for this 4 options, we use the first formula, this formula, and for the last one, we use this last formula. Therefore, here we have 10,000 times 1 plus, this is R, N is 1, because the compounding is annually, once a year, to the power of N times T. N is 1, so 1 times 5 is 5. Therefore, if we use our calculator to find this, we get something like this one, okay? And then for this one, it becomes A equals to 10,000, 1 plus 0.04. Here, N is 4. And here we have 4 times 5, which is 20, okay? And that becomes this will be over 4, 20, and this is 0.90. Okay. And similarly, we can find the next one, and that one we use 1 plus 0.04 over 12 to the power of 5 times 12, which is 60. And this becomes 20, or 12, 20. And this becomes 60. I'm using my calculator to find the result. 1229.97. And I will skip this one because they are more or less the same. Well, let's just find it out. Okay, for this one, A becomes 10,000, 1 plus 0.04 over 365 times 5 times 365. And this is, let me use my calculator. 0.893. Okay. And the last one is we will use this formula. The formula that we're going to use is P, which is 10,000, E, R is 0.04 times 5. And that becomes 0.027. Okay. So here we start with this number 12,166, and here it became 12,201, and as you can see, it's kind of increasing. And here 209, then here 213, and here 214. Okay, so as the compounding increases, the compounding time increases, then the interest is increasing, of course, right? So for when it's continuously, when the compounding is continuously, we have this one. And when it's daily, which is 365 times a year, then this is the value. And the difference is kind of small. It's less than $1. Yeah, it's less than $1, the difference. Okay. So this is one of the applications of this special number E, and of course it has more than this application, so it can be used in more other applications. Okay. All right, so this is all for today, and see you in the next lecture.